product of the direct hydration. It's Markovnikov product, and the addition of Syn and anti-addition, it's not applicable because you do have an intermediate that is a carbocation with no bridge, no restricted carbocation or intermediate. The problem with that is you have possibility of rearrangement, and the other problem is you have to use the strong acid, and using a strong acid, it can affect your organic molecule. So indirect hydration, which the net result still is addition of H and OH. One reaction we talked about the mechanism yesterday, and that was the oxymercuration demercuration. The product is anti-addition. There is no rearrangement because the intermediate is a restricted intermediate. You have the triangle formation of the intermediate has the triangular shape that both carbons, they were engaged. And now just the addition, so it's Markovnikov addition and anti-addition. For hydroboration-oxidation. For hydroboration-oxidation, the product is going to be Syn addition. That means if the H is added from this side, if the hydrogen is added from this side, the OH is going to also add it from the same side. So this is called the Syn addition. The addition, you see that OH is on carbon 1. This addition is anti-Markovnikov addition. One thing that I told you as a hint, I said if your reaction mixture contains peroxide, remember that is going to end up with the anti-Markovnikov addition reaction. That's when you're adding HBr and peroxide, or when you're doing hydroboration-oxidation, you are using a peroxide as the oxidizing agent here. So this is just a hint. There is really no rule, or is not a law, but is a hint that anytime you have this peroxide, your product is an anti-Markovnikov addition. Anytime you have a triangle as the intermediate, so if you had like a Br, or if you had the triangle of the Hg, for oxymercuration demercuration, the addition was anti-addition, but with the peroxide is anti-Markovnikov addition. The net result is addition of water. So you're starting with alkene, you end up with alcohol. The addition is a Syn addition from the same site, and addition is anti-Markovnikov. So anytime you want to make like primary alcohol, you have to think of hydroboration-oxidation. So formation of primary alcohol is not possible via oxymercuration, demercuration, or direct hydration. So the advantage of the hydroboration-oxidation is that you can make primary alcohol, or you can have the OH on least substituted carbon. The other advantage is that you don't have a chance for, the reaction doesn't have a chance for rearrangement either. So the carbon skeleton is going to stay the same, just like oxymercuration, demercuration. But you can make primary alcohol with this method. So BH3 or borane is going to act as, BH3 is acting as your nucleophile, then hydroxide is acting as the carbocation. It could rearrange. Okay, if the carbocation is restricted, it cannot rearrange. For hydroboration in the intermediate step, carbocation that forms an intermediate step for oxymercuration demercuration is this restricted carbocation. So you get the plus charge is restricted. So it's not one carbon is taking the plus charge. If you look at the mechanism for this reaction also, it's going to form a bridge, and it's forming a bridge, so it is restricted. So it's not, okay, it's forming a bridge also. So other points you work on. So other points, BH3 is the electrophile, and OH is the nucleophile. THF here is just the solvent, or basically it's going to stabilize the BH3 because BH3 is very unstable. Since BH3 is very unstable, they usually keep the BH3 in THF, which is a tetrahydrofuran. The tetrahydrofuran is going to have oxygens with pairs of unshared electron, which can stabilize the BH3. So BH3 THF combination is your starting material for this reaction. So THF, it's not reacting, but it's holding the BH3 stable. The numbers 1 and 2, what does it indicate? If you are separating two reactants by a comma, like here you have a hydroxide comma H2O2 comma H2O. When you are separating reactants or reagents by comma, that means the reagents are added at the same time. Or if you are separating the two reactants or two chemicals in the reactant with the slash, that means that they are being added at the same time. When you are separating the reagent sets or any reagent with numbers, what does that mean? You have 1 and 2. That means you have two-step reaction. You get a product from the first reaction, and then the product from the first reaction is going to be exposed to the second set of the reagent for the follow-up reaction. So you get one compound and then you get the other. So you have, let me bring a example. So if you have a alkene and you're adding H2O, this slash separating the two reactants from each other, that means these two are necessary to be added at the same time. So you're adding these two at the same time. So you will get carbocation in this case. You will get carbocation, but you are not separating the carbocation. You cannot isolate or tricarbocation. So carbocation is going to change to the final product. So you have a product here. But when you are doing oxymercuration demercuration, for oxymercuration demercuration, you are going to have, okay. For oxymercuration demercuration, you have your first set of reagent, HgOAc plus, and then second, you are going to do sodium borohydride. So first you get oxymercuration product, then you are going to get alcohol as the product. So you will get your OH, and then you have your HgOAc as the product. And the next step, when you are adding 2, you will get the alcohol as the product. So these are product. This is a product. Why do we call it product? There is no positive or negative charge. This is not an intermediate. But the top one, you have, this is an intermediate. That's an intermediate, is not a product. So when you are separating your reagent as 1 and 2, reagent set 1 is going to give the first product, and then your product is going to go through a second reaction with the second reagent set, and you will get your final product. So it's two-step reaction. That's the difference. And for hydroboration-oxidation, just like oxymercuration, demercuration, you have also two-step reaction. One, you add the BH3 THF, you get one product, and then second, you are going to add H2O2 OH and H2O. Mixture of this set is going to give you final product. Okay? So you have two steps. When the reagent sets are separated by number, you have two steps. And each step, it gives you a product. No mechanism. Is just know that the hydride is going to replace the HGOAC. Now, no specific reagent is needed for that mechanism. Okay, should have marked your work. Which slide number? So for hydroboration-oxidation, if you want to look at the mechanism for this reaction, the BH3 that is going to act as an electrophile. Hydrogen is going to attach to the least substituted carbon, and the BH3 is going to attach to more substituted carbon. So your nucleophile, and then you have your electrophile. So your nucleophile is going to attach to the CH, which is the more substituted carbon, and then electrophile is going to attach to the other carbon. On the next step, when you're doing oxidation, this oxidation is going to replace the OH with BH2. So the first set of reagent BH3 THF is going to make this product. Okay, is the alkyl borane. Alkyl borane is your product. And the next step, when you bring the hydrogen peroxide with the hydroxide, is going to oxidize this, and is going to replace the BH2 with OH. So when this is starting, it's coming as a bridge. So you see this is happening at the same time, and that's why addition is going to be Syn addition, because you can't separate this to come from the opposite side. It's not going to happen. So both addition is going to be from the same side. So this is called a Syn addition. So you have Syn addition, and is a anti-Markovnikov. Anti-Markovnikov. So for the alkyl borane, you can use alkyl borane instead of the borane itself. So it's just like it's going to act just like the borane, with exceptions that this is going to be it has only one hydrogen to replace or to add, and it's going to stop at just first step. So you would get the dialkyl borane as the product. Hydroboration-Oxidation, it gives you primary, and the rule is that electrophile is going to add to the least substituted carbon, and the nucleophile is going to add to the most substituted carbon. So the difference is that the carbon that is so you get anti-Markovnikov product. Then, like when it comes to reading, I can't keep up. So we're just gonna talk about this instead of reading. So BH3 THF, the first step is going to give you that alkyl borane or trialkyl borane, and then is going to, the second step is going to give you alcohol. So what you need to know, the net result, addition of OH to least substituted carbon and addition of hydrogen to the most substituted carbon. And similarly here, most substituted carbon is going to take the OH, I'm sorry, the H, and least substituted is going to take the OH for anti-Markovnikov product. Okay. I just want to make sure that, again, you know the reagent. You have two sets of reagent. Step 1, you do hydroboration. Your reagent is BH3 THF. Step 2, you have second set of the reagent. You need to know that this is a anti-Markovnikov addition. That means OH is added to the least substituted carbon. And also the addition for hydroboration-oxidation is going to be Syn addition. That means both of them are added from the same side of the molecule. Hydrogenation. Hydrogenation, that means adding hydrogen to alkene. The product is going to be alkane. Hydrogenation needs a catalyst. Your catalyst could be nickel, platinum, or palladium. Either one of these can work with the H2 and changes the alkene to alkane. The addition is the Markovnikov, anti-Markovnikov is not applicable here, right? Because both of the group attached, your electrophile and nucleophile that is attached here, is going to be hydrogen. So Markovnikov, anti-Markovnikov not applicable, but in terms of the, is it Syn addition or anti-addition, is going to be Syn addition also. So just remember that this is going to be Syn addition. So how is going to be Syn addition? Basically, alkene is going to attach to this solid. You have in either case you have a solid catalyst. So alkene is going to attach to the solid from. It has to attach from the same side because you cannot twist the molecule to come and attach from the opposite side to the solid catalyst. Then one hydrogen comes and bonds with one of the carbon, it kind of lifts it or separates from the solid, and then the second hydrogen from the same side is going to come and saturate or lifts the other carbon or separates the other carbon from the solid catalyst. The final product is alkane. Addition is Syn addition. So anti-Markovnikov, Markovnikov does not make any sense here. So this demonstration probably easier for you to see why is a Syn addition, because your alkene, the carbon-carbon double bond, is going to attach the surface of your solid catalyst. So it's going to form bond, and then hydrogens are acting at the surface of the catalyst. So one hydrogen, it comes and forms bond with this carbon, the other hydrogen comes forms with this carbon. So there is really no chance for this carbon to attach from this end to the catalyst and then the other carbon to attach from the other end, the other side. So in other words, your molecule cannot be twisted. So if it's attached to the solid surface of catalyst, it's attached from the same side and is going to be detached one at a time. The final product is going to be alkane. So all you have to do, just add the hydrogen to each of these carbon. That's the final product. So you're getting a hydrogen attached to each of these carbons. The overall reaction would be alkane. Yes, you're right. Okay, any questions about addition of HX? So when we say any questions about addition of HX, do you know that this addition is Markovnikov or anti-Markovnikov? Do you know if it's syn or anti addition? Does it make sense? Is it applicable or not? It's not applicable, syn or anti, because you get a carbocation with no restriction. So you will get the both. You can get both products. So you're not discussing is it going to be syn or anti addition. It's not applicable, both of them. So it's both. Addition of water, direct hydration, addition of alcohol. So you need to know the product of addition of water is alcohol. Addition of alcohol to carbon-carbon double bond, the product is ether. Both reactions are acid catalyzed. Addition of halogen, this is anti-addition. The intermediate was the bridge that you had for bromination, and because the intermediate is restricted, the other one is going to come from opposite side, then triangle is going to break. Halohydration, that means you're adding halogen and water. Also addition is anti-addition. Okay? Is anti-addition. Oxymercuration, demercuration, the product is alcohol, addition is anti-addition, and the product is a Markovnikov product. Okay. Expect a diagram like this on your test where you fill in all these reagents. What is going to be what are the reagents that will change your alkene to any of these products? Basically, summary of all of the reagents that you have learned about in this chapter. So you need to memorize all of the reagents. How do you go from alkene to epoxide? How would you go from alkene to primary alcohol? How would you go from alkene to alkane? And how would you go to secondary alcohol? Any questions? Which you have to memorize basically all the reagents. And as you're memorizing the reagents, just make sure that you put in your flashcard what type of addition this is. Is it anti-Markovnikov or Markovnikov? Because these are all addition reaction. What you mean by summary of all the addition reaction, that means a pi bond is going to break. So when the pi bond is going to break and it changes to 2 sigma bond, you have to add electrophile and a nucleophile to the carbon-carbon double bond in order to break the pi bond. That's why the reaction is called addition reaction. You're always adding something to this molecule. It's not like a substitution or elimination. This is addition reaction. So for all addition reaction, you need to know if the addition is going to be Markovnikov or anti-Markovnikov, is the addition is going to be syn or anti-addition, and what is your reagent, what are your products. Any questions? Addition of carbene. Carbene is the reagent for carbene is a CH2. So you have the pair of unshared electrons, and then you have a negative charge on it. So that is a carbene. Okay. So the general reaction is that your CH2 is going to come in. You see, CH2 is bringing pair of electron, and you have a pair of electron from carbon-carbon double bond. So basically you have 4 electrons that can form bond between the carbene as the incoming group and the CC double bond. So 4 electrons is going to be consumed, and you are going to get a triangle. So basically, addition of carbene, or the other name for this reaction is cyclopropanation. Basically, you are going to make cyclopropane from carbon-carbon double bond. Very similar to formation of epoxide structurally, but your reagent is different. So when you have your reagent of a carbene that coming in with the pair of unshared electron attacking the carbon-carbon double bond, the final answer is going to be formation of cyclopropane. So addition of carbene or cyclopropanation. The methods that is discussed here for the rest of the basic chapter is the methods that have to prepare carbene, because when you have the carbene, the addition is going to be they all follow the same method, so same pattern. You have your carbon-carbon double bond forming bond with the carbene, and it's going to form cyclopropane. So you need to recognize your reagent. One of the reagents that you can prepare the carbene is starting with diazomethane. Diazo, that means two nitrogens, and then you have the methane. The structure of the diazomethane, you have the NN CH2. Okay, NNCH2, when you expose to heat or light, this is the unstable compound. Diazomethane is not stable because if it goes to product, that it can decompose basically in presence of heat or light. When it decomposes, it's going to give you nitrogen, and nitrogen gas is it's highly formation of a nitrogen gas, because it's triple bond, is going to be highly exothermic. Basically, this is the reaction that is used, formation of N2 gas. Actually, it as a triple bond is the reaction that is used in like dynamite, reaction of dynamite, which is highly explosive. What does it mean? It means that highly exothermic. It generates lots of heat when they want to like do demolition or do like the building like roads in the middle of mountain. They can use this actually to make their job easier. So this is highly exothermic. That means this reaction can take place spontaneously. So diazomethane, it can generate the carbene because N2 is going to be released, and highly exothermic reaction, it can give you carbene. When you have the carbene, the question is solved because all you have to do is to generate the carbene, and then when you have the carbene with the CC double bond will give you a propane, cyclopropane. The methylene iodide with zinc copper as a catalyst can also can also generate carbene, and the other reaction is the alpha elimination of haloform. Alpha elimination of haloform is going to also give you carbene as the product. So methylene iodide with the zinc. So you can get this reaction, methylene iodide with zinc copper as the catalyst. It can generate the carbene. So haloform, alpha elimination of the haloform, it can also generate carbene. So what you need to know is just that the three different methods that you can use to generate carbene. What type of addition you are going to get? Addition, of course, is going to be from the, it's going to form a triangle. Okay, it's going to form triangle as the stereochemistry. So you get addition of the C in the same side, so it's going to be triangle. for the alpha elimination also. So what you need to know, just memorize your reagent. These are the reagents that can produce the CH2 carbene. It's missing 2 hydrogen, but it has pair of unshared electrons. So if you start with cis, you end up with cis. If you start with trans, you end up with trans product. So it's not going to change the stereochemistry because addition is going to add from the same site. It's not going to change the stereochemistry. That's another point you need to know for cyclopropionation. How to get the carbene and the stereochemistry is added from same site, obviously, and then it would retain the cis trans. If you start with trans, you end up with trans. If you start with cis, you end up with cis product. We already talked about epoxidation or formation of epoxide when you are using the proxy acid. With the proxy acid being very unstable compared to carboxylic acid, the oxygen that we have attached with a single bond to the other oxygen, this bond is very weak, unstable, and it's going to form a triangle and formation of epoxide. The other name for epoxide is oxidant. Epoxide or oxidant for that. There is a transition state here, no intermediate, so you have the transition state only that is going to give you basically releasing of one of these oxygens from the proxy acid into the changing to carboxylic acid, and you get your epoxide as a result. What about the epoxide stereochemistry? Epoxide stereochemistry also, because formation of triangle is going to be from the same site. So if it's cis, it will stay as cis. If it's trans, it will stay as trans, just like carbene. Any questions? For the last two reactions, I didn't go step-by-step mechanism, and I won't expect the step-by-step mechanism, but what you need to know, what is your reagent or how to generate that reagent in the reaction mixture for carbene, in the case of carbene, and what is the product, and how is the stereochemistry of the product. Basically, if you start for both case, formation of oxidant or formation of the cyclopropane, the stereochemistry is retained. Cis will give you cis and trans will give you trans. Okay, any questions? What happens if you add water to epoxide? If you add water to epoxide, when you add water, you basically are adding H and OH, right? So if you have a CC double bond, you add water, you're adding OH, and you're adding H. Now, if you have epoxide and you add water, if you have epoxide and you add water, you're adding H and you're adding OH. So if you add H, you already have oxygen. This is going to change to OH, and then you're adding OH. So basically, the product is going to change to diol. You get the OH and OH. This is called ring opening of epoxide. You start with epoxide, and then you add water, you hydrolyze it. It's going to change to diol. Now, is the product anti-addition or syn addition? Is it going to attach from the same side or both opposite side? Anti-addition. Okay, the hint for this is the presence of this triangle as like a restricted structure. So the mechanism for this reaction is the acid catalyzed reaction. First, you are going to protonate the oxygen, so you will get the H plus here. This is changing to very similar intermediate when you had the Br with the plus charge. Very similar. So what's going to happen, you're going to bring water. Next step, water is going to come in. It cannot come from the same side that you have restricted triangle. Is going to come from the opposite side. If it comes from the opposite side, it's going to form bond with one of these carbons, and the ring is going to open. So you have like protonated alcohol here. You have to remove the hydrogen with the plus charge. Remove the hydrogen with plus charge, you end up with the OH from on one side and OH on the opposite side. So you get the ring opens to the top, and then H2O is going to attack from the bottom. So it's an anti-diol. So OH is at from one side, and the other OH on the opposite side. If your reactant was not symmetrical, let's say you had a CH3 here, which way the diol is going to attack? The diol, the water is going to attack after you have this intermediate. Water is acting as a nucleophile, and your nucleophile is going to attack the most substituted carbon. So why is most substituted carbon? Because the plus charge is going to be more stable around this carbon, and since nucleophile is looking for plus charge, is going to attack this carbon here. So if you had a better group here, a better electron donor group on this side, then H2O would have attached to this carbon. So it depends on which area, which of the two carbon can handle the plus charge better, or the plus charge is found around which carbon more often. That's where you find your nucleophile attacking. Since we already had this with the other reactions of addition of Br and addition of the halohydrine or formation of halohydrine, it's very similar. So it's just for you to learn the pattern. Like when you bring acid catalyzed, what does it mean is acid catalyzed? That means that H plus is going to come in first. If H plus comes in first and you have epoxide, would the H go with the one of the two carbons or oxygen? There is really no benefit for H plus to come with these carbons because these carbons are already positive. But the oxygen has pairs of unshared electron still. That's why it's attracted by this H plus. So you protonate the oxygen and the epoxide, and then you kind of activate this ring because you have the plus charge in the ring now. Then you bring your nucleophile, which is looking for a positive charge. Which of these two carbons is going to be a good candidate for nucleophile is the one that can handle the plus charge greater or better, and that would be the plus charge on carbon that is more substituted carbon, because the CH3 is electron donor, is a G group, electron donor group. So the final product is formation of diol, and the addition is from opposite side. So it's anti-addition because of the backside attack that you get from the nucleophile. So after this is a plus charge here, the H2O is going to have a backside attack. If not symmetrical, look for more substituted carbon. Now, syn addition of the diol that has a different reagent, so is not the H2O plus H plus for plus acid or acidic water, is the osmium tetroxide, and based on the mechanism or the structure of osmium tetroxide, okay, you see that this is going to form the bridge again, and then you're going to break the bridge after you hydrolyze this. So first this bridge is going to form, is forming from the same site. So after you break the bridge, it's going to protonate both of these oxygen from the same site. The final addition or the net result is addition of OH on the same site of the molecule. So this is syn addition of the using osmium tetroxide. So when you are looking for the reagent set is the osmium tetroxide, it has to follow by hydrogen peroxide. So basically you are bringing hydrogen peroxide. The osmium tetroxide is going to leave later because that's not going to be consumed. It's used as a catalyst. So if you bring osmium tetroxide, then you would get syn addition of diol. You get the diol that is syn addition. Permanganate, also potassium permanganate, also if you add to CC double bond. It depends on the condition of the permanganate. Now, if the condition of the permanganate is the cold, is going to give you cold dilute is going to give you diol. If it's hot permanganate is going to cleave the carbon-carbon double bond. And when it does cleave the carbon-carbon double bond, you are going to get the CO double bond on each side of the CC double bond. Okay, so oxidative cleavage is going to happen. So it depends on you are using cold dilute permanganate or you are using hot concentrated or warm concentrated permanganate. If you're just adding cold dilute, you will get diol, and the addition is from the same site again, syn addition. If you are using hot permanganate, is a further oxidation. So further oxidation, if you have a COH changing to C double bond O, that's one level oxidation when you have one oxygen added to the carbon. Here you have a double bond oxygen because permanganate is a very strong oxidizing agent. When you add hot permanganate, it's going to go two-step oxidation. First is going to change to diol, but that's intermediate, is not going to stay like that, is going to change to CO double bond. Now, if your alkene, if the alkene is monosubstituted alkene, you have a CH3 here and the CH3 on that. There's a hydrogen and hydrogen. With the hot permanganate, it's going to add the CO double bond. So all you have to do, cleave the CC double bond, cleave it from here through the double bond, add oxygen to the left side, add oxygen double bond to the right side. The product is going to be 2-aldehyde. And it's 2-aldehyde because you have one hydrogen already on the CC double bond. Now, if your alkene is a highly substituted alkene, so you get 2 CH3 here. If you have 2 alkyl group attached to one carbon, then your product is going to be ketone. So if you have 4 alkyl group attached, you get 2 ketone as the product. So carbon carbon-carbon double bond with hot permanganate, the product is going to be either aldehyde or ketone. Now, if you get aldehyde it has still one hydrogen and the aldehyde. So if you get aldehyde, so if you have aldehyde as your final product, this can be oxidized again. What would be the product? Can you add another oxygen to this functional group of aldehyde? If you add oxygen to this group, basically you are changing your hydrogen to OH, so you get COOH. It gives you carboxylic acid. So if your product is aldehyde, it can go oxidation next step to carboxylic acid. If your product is ketone, and this is the product of oxidative cleavage of the permanganate, okay? If the product is ketone, is not going to oxidize further. So if you have ketone and you add permanganate, there's going to be no reaction. So if it's aldehyde with permanganate, even if it's hot, even if you heat it up, it's going to be no reaction. So ketone would stay as ketone, but aldehyde would change to carboxylic acid. These are, if you please pay attention, because this can be, you will them as a multiple choice exam question and the quiz question. So you have, when the oxidative cleavage happens here, there is a hydrogen on this carbon. So because there is a hydrogen on that carbon, this is going to change to aldehyde, first step, and then it would change to carboxylic acid as the final step. On the left side, the CC double bond, this carbon is attached to 2 carbon, and because it's attached to 2 carbon, it's going to change to ketone, and it will stay as ketone. So oxidative cleavage can give you either aldehyde or ketone, but if it gives you aldehyde, aldehyde is going to further oxidize to carboxylic acid. See that this is going to oxidize to carboxylic acid because there's a hydrogen attached. If there is no hydrogen attached to carbon, you cannot oxidize it. Like if you have a alcohol, primary alcohol, you can oxidize to ketone. If you have secondary alcohol, it can oxidize to primary alcohol to aldehyde, secondary alcohol to ketone. But if you have a tertiary alcohol, because there is no hydrogen attached to this carbon, is not going to oxidize. So if you bring oxidizing agent, there would be no reaction. Just like ketone, because there is no hydrogen attached to carbonyl group, is not going to oxidize further, but aldehyde can oxidize further. What happens if you have a cyclic alkene? With the cyclic alkene, you have this, and you are going to expose to KMnO4. If the KMnO4 is dilute and is cold, you get OH on each of these carbons. If it's warm and concentrated and you apply heat, it's going to give you oxidative cleavage, is going to break the ring. You get a CO double bond on each side, but since you have hydrogen here, you have a hydrogen here, both of these carbons is going to change to carboxylic acid functional group. So your product is going to be, you have 6 carbon, 1, 2, 3, 4, 5, 6 carbon, and then each one is going to carry COOH. So basically you are getting a compound with 2 acid functional group. So that's also a ring opening, but this is ring opening alkene if you use hot permanganate, or you do ozonolysis. Ozonolysis is another reagent that can do the same thing. It opens the ring, or it cleaves CC double bond and then oxidize both. If you don't have hydrogen here, it will stay as ketone. If you have hydrogen attached to CC double bond, or any of the sp2 carbon, if they carry a hydrogen, it can be oxidized to carboxylic acid. So in oxidative cleavage of alkene with hot manganate, if the sp2 carbon carries hydrogen, the product of that side is going to be carboxylic acid. If the sp2 carbon has no hydrogen, the product of that side is going to be ketone. And you are going to have to do a few practices in order to memorize all this, but at least, you know, the hints that I'm giving you, trying to help you to memorize. Next reaction, ozonolysis. There are a lot of reactions in chapter 8. Next reaction is ozonolysis. What is the product of ozonolysis, or how this is going to react with alkene? Just like hot permanganate, it's going to cut through carbon-carbon double bond. This side of the molecule has hydrogen, is going to change to aldehyde. One side of the molecule that is no hydrogen, it will change to ketone. Now, depends on solvent that you are using for ozonolysis. The solvent that you are using, if it's dimethyl sulfide, your aldehyde would stay as aldehyde, is not going to change to carboxylic acid. Because what happens to this? This is going to capture one of these oxygen from the ozone. So you have the 3 oxygen here. One would go to ketone, one would go to aldehyde, and one would change that solvent that you have to sulfoxide. So it's going to, the dimethyl sulfide would change to dimethyl sulfoxide, and you're going to keep the aldehyde as aldehyde. So if you have a multiple choice question, and in your multiple choice question, this part is missing, it's just one arrow, and it's giving this reactant to the product. If your product stays in aldehyde, you see that a cleavage has taken place. So you have two possible reagents so far. One is permanganate, the other one is ozonolysis. Which one is the better choice? If the aldehyde stays as aldehyde, that means you have used ozonolysis. If aldehyde is not there and it's changed to carboxylic acid, ozonolysis cannot work. You have to use hot permanganate, or permanganate concentrated and hot. Okay. So ozonolysis is milder than hot permanganate or concentrated permanganate. For ozonolysis, actually, if you use dimethyl sulfide, it's going to, because later on, if you don't use dimethyl sulfide, you learn in next chapter that if your solvent is not dimethyl sulfide, it can go further and it can change to carboxylic acid. So overall reaction with the ozonolysis, you're going to get aldehyde, ketone, and your dimethyl sulfide would change to dimethyl sulfoxide. If you hear about DMSO, that's dimethyl sulfoxide. This is a aprotic solvent. Is an aprotic solvent that could be used SN2 reaction as well. Is a polar but aprotic solvent. The ozonide, this intermediate, is not going to be isolated. So you start with the alkene, and you start with the alkene, and you end up with the aldehydes and ketones. So this intermediate is not going to be separated, so it's not stable. Questions? There are a lot of reactions, and I understand that you are going to have challenging time to memorize them all, but if you memorize them all, it's going to set you up for Organic 1 to do well, for quiz for Chapter 8 and exam 3, and everything that you need to know for Organic 2. With just the reagents is going to change. But a lot of this is going to be first chapter of your Organic 2. So you want to memorize it all. Know what is the reagent, what is the product, know if the addition is anti-addition or syn addition, is the addition is Markovnikov or is it anti-Markovnikov, or what reagent you need to pick to get Markovnikov, what reagent you need to pick when you have choices to get the anti-Markovnikov. When you start with alkene, if you want to do oxidative cleavage, if your product is carboxylic acid, you must use hot permanganate. If you want to keep it as the aldehyde, you have to stop with the aldehyde. Then you use milder oxidizing agent, and a mild oxidizing agent in that case is ozonolysis with the presence of dimethyl sulfide. Okay. A last reaction of this chapter, or alkene, which we also saw it in the first or second, or it was previous chapter. We had a summary of the reaction. Polymerization was introduced there. So if you start with the alkene, you can polymerize that. And here is just showing how the catalyst is working to initiate the polymerization. So polymerization, if you have carbon-carbon, let's say you have a carbon-carbon double bond, and use a catalyst of, sorry, I was trying to change the color and erase it. So if you have a CC double bond and you bring H plus, it can change this to carbocation, so you get H and you get your carbocation here. Now to this carbocation, if you don't bring any other reactants in the file, and you set it to have, it's use another CC double bond. So this is trying to form bond. The carbon is trying to form bond with the CC double bond. So it's going to attack this. Basically, it should be the opposite. So what you are doing always from electron rich to electron poor. So this pair of electrons is going to come and form bond between carbon and carbon. What's going to happen to the other carbon? What will happen to this carbon? If the pair of electrons is coming to form new bond here, what's going to happen to the other carbon? A new bond is forming here, and the other carbon is taking the plus charge. Do you have a product at this point? No. It still is intermediate, right? So this intermediate, if is going to react with another alkene, because this is your monomer, is going to react with another alkene plus the CC double bond. What's going to happen? This is just a double bond. What's going to happen here is that the pi bond will form bond with the carbocation, is used to form bond between one of these carbon from the alkene with the carbocation, the other carbon will take the plus charge. Now you end up with the next intermediate. How many carbons you have on the next intermediate? You start with 2 carbon. After adding another unit, you end up with 4 carbon, carbocation with 4 carbon. You are adding another CC double bond. You end up with carbocation with 6 carbon. And if you continue with another CC double bond, you end up with carbocation with 8 carbon. And then it just, every time you are repeating this reaction, is going to add 2 more carbon, and you get intermediate. So basically, when you are making like slime, or they're making like plastic, the reaction doesn't take long, because it's like continuous reaction, is like a chain reaction. Is one carbocation is consumed, another carbocation is produced. One carbocation consumed, another carbocation is produced, which is like a larger carbocation. So you get 2, 4, 5, 6, 7, and 8 carbon, but still is carbocation. At what time, under what condition this reaction is going to stop? You either have no more of alkene, that this reaction is going to stop because you don't have any more alkene, or you are going to stop the reaction. To stop the reaction, you have to bring like an inhibitor, but you can also make sure that this reaction is going to continue until the reactant is consumed entire. So an alkene, which is a monomer, it can add to another molecule like itself to form a chain or is a polymer. You see that every time is adding 2 carbon, and then you get another carbocation, and just adds 2 more carbon, and you get another carbocation. So cationic, the carbocation intermediate, that's the example that I have here. You bring like acid catalyst to generate the first carbocation, and the carbocation is going to attack the alkene. It produces more carbocation. You could have free radical, or you could have a anion intermediate, carbanion intermediate, which it says is rare. So for free radical, what do you need to bring in to make a free radical? If you were going to change this to free radical, you have to start with the free radical first. So the best thing would be to bring a peroxide. A peroxide is going to generate a free radical. So it's going to give you free radical. And when this is added to CC double bond to begin the reaction, is going to take one of these electrons only. So you end up with RO, C, and the other carbon will change to free radical. So you get 1 electron from the carbon, 1 electron from this free radical to form this new bond. The other carbon will be free radical. Now this can attack another CC double bond. Same thing is going to repeat over and over. And then every time is adding 2 extra carbon. So you start with the first alkene, you get your dimer carbocation, your dimer carbocation adds another one, you get a trimer, and then it would, if it continues, then you will get your polymer. Your termination step, that's the same thing that I said, when is going to stop this reaction. In the termination step, you have to bring a nucleophile to react with the carbocation to stop the reaction, or you have to bring an inhibitor, some sort of inhibitor. So last step, you can get the elimination reaction, like a E2 type reaction. So if hydrogen is removed, and you end up with CC double bond at the end of the chain, because it has to stop, the reaction has to stop. Questions? Any questions? Okay. I haven't looked at the schedule, really. The I haven't looked at the schedule. When is your quiz? Is it today? It's supposed to be today? Today. Do you want me to keep it for today or move it to tomorrow? Tomorrow? I hope nobody is scheduled, you don't have other exams or other assignments that it's conflicting with the quiz tomorrow. You learn the reactions, many reactions today. I want you to do practice. I want you to finish your OR assignment before you take, ideally, finish it all before you take your quiz. So that's why I want to give you time to finish your OR assignment for chapter 8 and then take the quiz. So I'm going to make the quiz available tomorrow. Yes. So make sure you finish the OR assignment before you take your quiz. Okay, you have chapter 8, 9, and 10. So I'm going to make one of them responders, monitor, and then 2 honor lock. Which one do you want to keep it as? You don't know the other chapters yet, so chapter 8, I'm going to go with the honor lock for chapter 8. We have actually 2 more quizzes. We have chapter 8, 9, 10, and then 1 extra quiz. So it would replace your lowest grade. So I have 2 honor lock and 2 more of the response lockdown browser. Okay. Chapter 8 is not hard, but is a lot. It has a lot of reactions because it's the first chapter that actually introduces new concept reaction, the preparation of the compound with different functional groups. It's if you are starting with alkene, you can get to alkyl halide, you could get to alkane, you could get to alcohol, you could get to ether, you could get to polymer, you could get to aldehyde, ketone. So you need to know the reagents and you need to know what is the addition. So, but if you do the OR assignments, it's going to prepare you for the exam. So I'm going to have 2 honor lock and 2 of the responders. So I let you know. So I'm not going to give that answer right now. I decide when I'm posting the answer. posting the quiz for you. So you might be on a rock, you may not be on a rock. Next chapter. Next chapter is a chapter of alkane, and alkyne. We just send a message. The alkyne is you need to know about functional group first. Functional group for alkyne is CC triple bond. So what else do you expect to learn from alkyne? Can you tell me what else you need to know about alkyne? First is functional group, is a CC triple bond. And knowing the hybridization, which is the sp hybrid. What else do you need to know? So when you are studying a new family of organic compounds, what do you need to know about them? I want to make sure this is a routine, and when you are studying, you do the same. You are looking for the 4 aspects that I keep repeating about. Preparation, how to prepare alkyne. The mechanism itself is not a concept, but is involved in both either preparation or involved in the reaction. So you need to know naming. Okay. So you need to know the functional group, physical property. You need to know about nomenclature, naming these compounds, how to name the compound, how to prepare these compounds, and there is one more. When you are preparing, alkyne is product on a chemical reaction, right? Okay, properties, which means the physical property. We're still having one more. So the hybridization or structure, which is going to affect physical property. Nomenclature, because you need to know how to name the chemicals. How to prepare when alkyne is a product. So you start with a reactant and you end up with alkyne as a product. Reactions of alkyne, when alkyne is a reactant and then you end up with a product. So what can you do with alkyne? What else you can prepare if you start with alkyne? So hybridization is sp on the carbon that carries the triple bond. General formula for alkyne is a CnH2n-2. So if you have 3 carbon, the number of hydrogen is going to be 4. Basically 2 elements of unsaturation, because for a saturated alkyne with 3 carbon, you end up with 8. You must have 8 hydrogen if it's an alkane. For alkyne, you have 4 hydrogen less, and that is a 2n-2. In this case, you had a 2n+2. So that's the general formula for alkyne. For nomenclature, the ending is YNE for alkyne, the family name. The prefix is the number of carbon you have. So if you have 4 carbon alkyne, you have butene, sorry, YNE, butene. The location must be indicated. Is this terminal alkyne or is the internal alkyne? So it's going to be 1-butene. For the name is going to be 1-butene. But means 4 carbon. YNE means that there is a triple bond, and 1 means that you have that triple bond starts with number 1. Just like alkenes, you don't have to say 1, 2. When you say 1, 2, that's like there's a triple bond on 1 and then triple bond on 2. So when you say 1, it's understood that triple bond starts there with the carbon. Is the functional group. So if you have branches here, you cannot start numbering from the left because the functional group takes the priority. So you have to number the carbon chain from the side that is closer to the functional group, which is the triple bond. Then you give the name for branches first with the location of the branch. Then you give location for the functional group or the triple bond and the name for the compound. When you have more than one functional group, then you have more responsibility. Now you have to give priority to this functional group. Which one takes priority? Between alkene and alkyne, you may not expect this, but alkene has higher priority. Alkene has higher priority. Between alcohol and alkyne, alcohol has higher priority. So this is when alkyne facing other functional group with higher priority. Ether has lower priority compared to alkyne. Alkyl halide has lower priority compared to alkyne. So you start with alkane, and then it's going to be alkyl halides, ethers, then is alkyne, then is alkene, then is alcohol. Alcohol has higher priority compared to alkene as well. So when you have the priority list, so you have the additional groups that is combined, you have to make sure you have to get the priority list first. When you have the alcohol with triple bond, alcohol takes the priority. So you have to decide which one is going to take the priority. And if you, after you decide which one takes the priority, then you can start numbering. Okay. The side. So in this case, you have to number from the left side because alkene is closer to the left side. So it's going to be 2, 3, and then 4, 5. The new and old naming, this is not like very old. This is coming from this new naming. It's starting 1997. They actually started this new naming. So it's not too old, and maybe few of you have been, born that time. So it's not that old or that new. Just remember, when I was teaching 1997 at Miami-Dade, that year actually this was the new addition to organic. At that time it was very new. Now it's like 20 years old, more than 20 years old anyway. So you can separate the functional group. So you first bring the number of carbon and then bring the functional group with the location, or you can use the high priority functional group and then continue with the low priority functional group as a separate functional group. Okay, so because you have two of the functional group at the same time. Both of them are acceptable, though. Both of them are IUPAC naming and still acceptable, both. So branches always should come first. So you have 2-methyl first, and then functional group is a ene and ine. So you have 1 pentene and 3 ine. So you cannot say 1 pentene, 1 pentyne. So you just say 1 pentene and then 3 ine. 1 pentene, 3 ine. So you have 3 butene, 2 ol. But OH takes the priority. That's why you number from the left side. If you want to name this as alkyne, so you would say 3 butene, 2 ol. This is a branch, so it's a methoxy branch. So you have, how does it change to methoxy? You have methanol, CH3OH. If you take the hydrogen away, this is going to change to methoxy. So you get the methoxy. It's like H2O, you remove one hydrogen, it changes to like hydroxy. So this is a methoxy. Etoxy. So if you have ethanol losing one hydrogen, is going to change to etoxy. Etoxy. No space, so etoxy. Okay. Common names are not used often. You just have to like recognize it. But the other terminology that can be differentiated here, this is a terminal alkyne, and this is a internal alkyne. For terminal alkyne, you have a hydrogen attached to sp hybrid carbon. For internal alkyne, there is no hydrogen attached to the sp hybrid. So when we are talking about acidity later on, the acidity it only applies to terminal alkyne because these do not have any hydrogens to discuss the acidity. I'm not sure your question was about which of these, but I brought it back. Yes, pentene and iron. To pentene, 1 pentene, 3 iron. Physical property, these compounds are not soluble in water because they are still nonpolar compound. They are hydrocarbon. All hydrocarbons are nonpolar and they don't dissolve in water. They are soluble in organic solvent as a result. The boiling point for this compound is low because it's nonpolar. Then nonpolar means you only have van der Waals forces. If it's polar, you could have dipole-dipole. If it has OH group, like alcohol, you would have hydrogen bonding. Or if you have two OH group, in terms of the diols, it's going to have 2 hydrogen bonding per molecule. Or if you have NH, is hydrogen bonding. But if you have only nonpolar compound, if it's a hydrocarbon, van der Waals forces is weak, and as a result is going to have low boiling point compared to alcohols, compared to carboxylic acid, compared to ketone and aldehyde, or compared to any organic molecule with polar functional group. They are less dense than water, and the up to 4 carbon is gas at room temperature. As you increase the carbon chain, because the molecule gets heavier, van der Waals forces or London dispersion is going to increase, and the London dispersion that increases, it can then change to liquid, and for greater carbon chain, the size of carbon chain, it can change to solid. So it depends on the molar mass of the compound. Uses, acetylene is used in welding torches. It can produce up to 2800 degrees Celsius. Why is so highly exothermic? It's a highly exothermic because it can produce lots of heat. Because you are breaking pi bonds and you're breaking all these pi bonds, and you're adding, let's say if you're adding sigma bonds to that, is going to get highly exothermic and produces lots of heat. Okay, it can be, they are adding acetone and fire bricks to keep the temperature controllable, so it doesn't melt everything that is carrying the flame there. How do they synthesize acetylene? In the serial method of synthesis, you add carbon with calcium oxide. Carbon plus calcium oxide, it would give you calcium carbide. The calcium carbide with water, it would produce acetylene. This is the industrial method of preparation of acetylene. After you have the acetylene, then you can increase the carbon chain. From the acetylene, you can keep the triple bond. If you remove one of these hydrogens, it's going to be negative charge, and it can act as a nucleophile with the alkyl halide, which I'm going to show you the reaction. But to prepare the acetylene, you start with the non-organic. You start with carbon, and you start with calcium oxide, which gives you calcium carbide, and the calcium carbide with water will give you acetylene as the product. So one of the applications of this, it was to generate the light for the miners. sp hybridization for acetylene. We talked about the sp hybridization before. You have one sigma bond and two pi bond, and the two pi bond is also counts for two elements of unsaturation. The bond length is going to be shorter. The strength of the bond is going to be stronger. So if you're talking about the bond length for single bond, double bond, triple bond, single bond is going to be longer than double bond than the triple bond. But if you're talking about the strength of the bond, triple bond is stronger than double bond than the single bond. Acidity, terminal alkyne, they are much more acidic than the alkene or the alkane. So if you compare the pKa, we talked about pKa before. What does pKa represent? pKa is very similar to pH. So if you're talking about pH or pKa, the smaller the number, the stronger the acid. So if you compare the terminal alkyne, and we have to have terminal alkyne because we have to have the hydrogen, with the alkene or alkane, you are talking about 25, 44, and 50. 25 is much stronger than the alkane, which is pKa of 50. So it's more stronger than the ammonia, but is not as strong as alcohols, because for alcohol, your OH is more ionizable. The H in OH is more ionizable compared to the CH from triple bond. But compared to hydrocarbons, it's one of the strongest acids for the hydrocarbon, which you have only carbon and hydrogen. So terminal alkyne is more acidic than all other hydrocarbons because of the higher S character you have for the hybridization. So as a result, they'll be deprotonated. So if if this hydrogen is acidic, the benefit of that would be you can bring a base and remove this hydrogen. So if you bring amide, which is NH2, amide is the conjugate base to a weak base. So if you start with NH3, which has a basic structure, if you remove one of these hydrogen, change it to NH2, your NH2 is going to be very strong base. So you get your NH2 minus very strong base. NH2 as a strong base can remove the hydrogen, and then you get your acetanilide ion. What is unique about acetanilide ion? Your acetanilide ion, carbon has negative charge. That means carbon can act as this carbon, or this unit now can act as a nucleophile. So when you are doing nucleophilic substitution reaction, you could use this as a nucleophile. So let's say you have CH3, C triple bond, C with negative charge. That's your acetanilide ion. If you add that to ethyl bromide, what's going to happen? So this is a strong nucleophile now. What type of reaction do you expect there? Synthesis. What would be the mechanism? Very good. Yes, it's going to be synthesis. What would be the mechanism? For the mechanism, you see you have a alkyl halide here is a primary alkyl halide. Your leaving group is a good leaving group here. You have a good leaving group and you have your alkyl halide, primary alkyl halide. You have a nucleophile here. So what is the mechanism? And if I classify this is like more hint, chapter 6, right? Strong nucleophile, good leaving group, primary alkyl halide. What else do you need to know to give me mechanism? What would be mechanism for this reaction? SN2. SN2 mechanism. So mechanism is SN2. What's going to happen? The nucleophile is going to form bond with this carbon. The leaving group is going to leave, and you end up with another kind. Now instead of 3 carbon chain, you have 5 carbon chain. So that counts as synthesis for alkyne, preparation of alkyne. For acetylene, you start with carbon. Okay, for acetylene, you start with carbon. But for anything, for other alkyne, you can start with the alkyne with a smaller chain, mix it with amide to remove the hydrogen. You get the carboanion, or you get the acetylenide ion, which is the negative with the negative charge. It can act as nucleophile. Now you can make this one to react with alkyl halide, and especially if it's a primary alkyl halide, is going to be fast reaction because this is a strong nucleophile. With the primary alkyl halide, you can add more carbon to this end. How many carbon? Depends what they told you. If they told you to make alkyne with 8 carbon, you already have 4 here. You bring the butyl bromide, and then with the butyl bromide, you are going to add 4 more carbon here. If you want to make alkyne with 7 carbon, you only bring alkyl halide with 3 carbon. Just remember, the strong base is going to remove hydrogen that is attached to sp3 carbon only. If your alkyne is an internal alkyne, that means there is no hydrogen attached to the CC triple bond, is not going to react with the because there is no acidic hydrogen to be removed. So when you have your acetanilide ion, you can add alkyl halide, your leaving group is going to leave and then would be increased in carbon chain. So this is the method for preparation. The mechanism of the reaction is going to be SN2, and you need a alkyl halide that is not hindered. It's either methyl halide or you would use a primary halide, because they are strong bases, also a strong nucleophile. Let me read the question. I didn't get it. Let me read it again. Would that negative or negate its ability to synthesize again? As long as it stays terminal alkyne. As long as it stays terminal alkyne. So you have to have a CC triple bond attached to hydrogen in order to add NH2 minus. So NH2 minus, of course, you don't buy NH2 minus, you buy it like as a sodium amide. But since it's ionic, it's highly, 100% dissociated, so you only use the NH2 minus. It can remove the H. But as soon as this changes to internal, you bring the carbon here, then it's no reaction, so the reaction will stop. So if you want to make a carbon chain longer than that, you have to start with the acetylene. So if it's acetylene, you can remove this hydrogen once, add the alkyl group, replace it with the alkyl group. You can remove this other hydrogen for second time, and then add alkyl group to this side. Okay. Okay. For this example, when you are trying to make the decyne from acetylene, 3-decyne from acetylene, first thing for you is to draw the structural formula for decyne, because it's 3-decyne. What is it? You draw the structural formula or condensed formula for decyne, that's your product, and then you do retrosynthesis. You say that we start with the acetylene, so we have added one R group that has 2 carbon, and another R group that has 6 carbon. Then you know what to add in each step. Sodium amide is going to stay constant. That's the base that you need to remove the hydrogen. You want to add 6 carbon, so you just add the 6 carbon halide. So you would use a hexyl bromide or 1-bromohexane. So you add your 6 carbon first, but you have to start with this. You have to know what product you are going to make first. So you start with this, and then you are going to add the 6 carbon. Now you bring another amide again, you remove the other hydrogen, and you add 2 carbon. Now you need the ethyl bromide. So hexyl bromide or 1-bromohexane or bromoethane. You just is like a retrosynthesis. After you survive chapter 8, these reactions are easier. But in order to understand some of the elimination reaction to produce this, you have to make sure that you know your chapter 6 and chapter 8 reactions. Okay? If you learn chapter 6, you learn chapter 8, then reactions for chapter 9 and 10 becomes very easy. So as a nucleophile is looking for nucleus, anything that with positive center, it can be the target for this nucleophile. If it attacks a carbonyl group, carbon has a plus charge, and then pi bond is going to break over the oxygen. Then you can protonate this, and you can make actually alcohol from the carbonyl group. Okay. Now, if depends on you have R groups here. If these are hydrogens, you make primary alcohol. If it's aldehyde, you could make secondary. If it's a ketone, you will make a tertiary alcohol. So it depends on what type of carbonyl group you are dealing with. But the net result is addition of nucleophile to the carbonyl group, the carbon of the carbonyl group, pi bond break over the oxygen, and you protonate this using water. You protonate this, it changes to alcohol functional group. Okay, I'm going to stop here. So if you just know that if you add this to aldehyde, it will give you secondary alcohol. If you add to ketone, it will give you tertiary alcohol, because this is going to be preparation reaction that you learn in chapter 10 again for preparation of alcohols. So these are all like kind of chain reactions. So SN2 reaction in chapter 6 you learned as a brand new reaction, but in this chapter you are learning SN2 again as a preparation for alkyne. So it's a continuous. If there is any of the chapters that you think you did not understand well, make sure you go back and review it again. Make sure you have a strong and good understanding of the previous chapters before you continue. It's just going to make your life much easier, and you don't find the chapter 9 challenging if you already know chapter 6 and you know chapter 8. So it's going to be very similar reactions, because in chapter 6 you learn a major type of reaction, which is substitution, and in chapter 8 you learn another major reaction, which is called addition reaction. So for substitution and addition reaction, those are two major type of reactions. If you learn now about the substitution and addition reaction, anytime you are making synthesis, it could be that. Then we only learn two new types of reaction in general, is the oxidation and reduction. So it makes it much easier. You already have learned about two type of reactions. Just make sure that you are pro on those two. Any questions? I'm sorry I got too excited about the new chapter.